Okay, first problem of this section 3.18 tells us to apply equation 3.73, which is the change of an expectation value with respect to time equation that we derived here, in the following four cases where the operator that we are trying to find the expectation values change in time is equal to either 1, the Hamiltonian operator, x, or p. And in each case, we're asked then to comment on the result with particular reference to the following four equations: 1.27, 1.33, 1.38, and 2.21. So 1.27 is this expression, d by dt of the integral from negative infinity to positive infinity of mag psi squared dx equals 0, which is basically saying that, the total area underneath a probability curve won't change with respect to time. This is directly used in the problem back in chapter 1, which asked us to show that if a wave function was normalized, then it would stay normalized with respect to time. 1.33 is an alternate way of writing the expectation value of p as mass times velocity, or in this case velocity being turned into derivative with respect to time of the expectation value of x. 1.38 is the relation between the expectation value of p and the expectation value of the partial of the potential energy with respect to x. And then finally, 2.21 is the expectation value of the Hamiltonian, aka the energy of the system, expressed as a summation of the individual probabilities of each energy, expressed as magnitude Cn squared, which in turn is an indirect statement of the conservation of energy. So lots of equations that we're asked to work with here. Let's start immediately just with part A, which is to say, okay, suppose that Q is equal to 1. And, there's not really any operator that is just equal to 1. But if there was one, then its rate of change would be based on 3.73. So let's write that out fully now in terms of Q being equal to 1. So d by dt of our expectation value of Q is going to be I over h bar times the expectation of the commutator between the Hamiltonian and our new Q operator, which turns out to just be 1, plus the expectation of the partial of our Q hat operator, which is still 1 over dt. And immediately, this thing is 0, right? Because 1 is just 1, it's a constant. Derive it by anything, and it's just going to give you 0. Same thing here, right? The Hamiltonian is going to commute with this because this is literally just a constant. It by definition will commute with any operator whatsoever. So this also is going to equal 0. Therefore, the rate of change in time of this expectation value of Q when Q equals 1 is equal to 0. Now, we can relate this to 1.27 directly because, remember, if we think about the actual equation of an expectation value, this can be rewritten sort of as d by dt of the integral from negative infinity to infinity of psi star Q hat acting on psi, right? And since Q hat is just 1, this is just going to go directly to d by dt integral from negative infinity to infinity of mag psi squared dx, and this is going to equal 0, which is exactly what we got over here. So therefore, if we just plug an arbitrary constant into our system that doesn't really represent an operator or anything, we get back to this statement, which is that, the area underneath the curve remains constant with respect to time, indirectly then implying that proof that we were trying to get way back in chapter 1 when we did this problem, which asked to show us that, if a wave function is already normalized, it's going to stay normalized over time. It's not going to suddenly denormalize unless we actually start introducing some crazy external factors into it. But as long as it's left alone, it remains normalized. And with that, let's jump to part B. Okay, part B is going to ask us to do the same thing, but this time Q is equal to the Hamiltonian. So now we're trying to find the rate and change of the expectation value of energy in the system with respect to time. So d by dt of the expectation value of h is going to equal I over h bar, expectation of the commutator between h and itself this time, plus the expectation value of the partial of h operator with respect to time. So this is automatically 0 because it's just the commutator of h with itself, which is just going to be 0 because if it's the same operators, it is going to commute with itself either way. This term is also going to go to 0 because h hat has no explicit time dependency. Remember, it's any operator that is physically realizable can be decomposed into something purely in terms of x and p operators, and since x and p don't have any time dependence, any physically measurable operator is also not going to have any explicit time dependence. So 90% of the time, or pretty much 100% of the time, this term is always just going to equal 0 no matter what. So what this ultimately tells us is that d by dt of the expectation of our Hamiltonian is just 0, which is directly just the statement of energy conservation, right? The energy of a system remains constant over time unless we start to exert some sort of force onto the system. In this case, this is an isolated system, or we're assuming it's an isolated system. So because of that, the energy remains constant and unchanged. And that is our very simple part B. Let's move on to part C. Okay, this is going to be our first non-trivial one. So if Q equals x, now we're trying to find the rate in change in time of the expectation value of position of the system. So d by dt of the expectation value of x is now going to equal I over h bar times the expectation of the commutator of h hat with respect to x plus the partial of x hat with respect to time expectation value, apologies. Okay, so automatically this thing is going to equal 0 again because x has no explicit time dependency. What we are concerned about finding now is this thing. So first off, let's rewrite this in terms of integral notation. So this is going to be I over h bar, integral from negative infinity to positive infinity. Our h hat operator is going to be negative h bar over 2m d2 by dx squared plus v. This is acting on x minus x acting on negative h bar over 2m d2 by dx squared plus v. All this acting on psi dx, and let's add the psi star that I forgot about here, and then close everything here in a bracket because that's all acting on psi ultimately. Okay, now let's use a bit of sort of distributive property and get this out fully. So this is going to be, let's see, negative h bar over 2m times d2 by dx squared of x psi, right, plus vx psi, plus, because the two negatives here make a positive, so plus x h bar over 2m d2 psi by dx squared minus x v psi, I believe. And in that case, these two terms cancel out. What we're left with is negative h bar over 2m times d by dx using chain rule. So psi plus x d psi by dx. And then this is going to be added with x h bar over 2m d2 psi by dx squared. Is that correct? Box prime times triangle plus triangle prime times box. Yeah. Okay. And this is going to be minus h bar over 2m. Apply a second derivative. This is going to give me d psi by dx plus d psi by dx plus x d2 psi by dx squared. We're going to add x h bar over 2m d2 psi by dx squared. Okay. Immediately I'm going to see, okay, this term cancels with this term. So what we have left is these two terms add with a 2 that cancels with a 2 at the top. So we have negative h bar d psi by dx all over m, like that. So in that case, if we plug that back in, right, this is going to equal I over h bar times integral from negative infinity to infinity of psi star times negative h bar over m times partial psi partial x dx. Move that to the front, or the constants. The h bars cancel. We're left with negative I over m, integral from negative infinity to infinity. Negative I over m, integral from negative infinity to infinity, psi star partial psi with respect to x dx. And this makes me think that maybe I left out an h bar somewhere. So please give me 1 second. I tend to mess up my algebra quite often. Okay, that's where I messed up. Just a very stupid mistake. The Hamiltonian operator has an h-bar squared instead of just h-bar on its own, so moving that over, this is going to be an h-bar squared term, so this h-bar still carries over like that. There we go. Okay, now, because of the fact that our momentum operator is equal to negative I h-bar d by dx, right? This is actually equal to 1 over m times integral negative infinity to infinity of psi star p hat acting on psi, like that. In which case this is equal to the expectation value of p divided by the mass. And this is specifically just equal to the expectation of velocity. So, you know, that makes sense, right? D by dt of the expectation value of x is equal to the expectation value of velocity. This is exactly what we showed way back in chapter 1, and this is also, I believe, one of these expressions. Yeah, this right here, right? 1.33. So we've linked it back to one of the earlier expressions that we were told to, and with that, we're done with part C. Let's move on to the final part, part D. Okay, finally part D, which is going to be the most mathematically annoying one to do, because we're going to have to do a commutator between h hat and p hat, which isn't fun. So the change in time of the expectation value of momentum for the system is going to be I over h bar. Expectation of the commutator of h hat and p hat added with the expectation value of partial p hat with respect to time. Once again, this has no explicit time dependence, just goes to 0. What we have left is I over h bar and the integral from negative infinity to infinity of psi star, and then the the commutator of negative h bar squared over 2m partial squared with respect to x squared plus v with negative I h bar d by dx. This is all acting on psi. So let's isolate this and try to work it out as neatly as possible. So let's see. Negative h bar squared over 2m partial squared by partial x squared plus v. Oh god, this is not going to be fun to write out. Let's change the brackets real quick. Okay, this times negative I h bar d by dx, and then subtracted by negative I h bar d by dx acting on negative h bar squared 2m d2 by dx squared plus v, and everything here acting on psi. Okay, let's move the psi's in. So let's see. Oh god, negative h bar squared over 2m second partial with respect to x squared plus v. And then this is acting on negative I h bar partial psi with respect to x minus negative I h bar partial with respect to x negative h bar squared over 2m d2 psi by dx squared plus v psi, like that. Okay. Now let's distribute again. So this is going to be, let's see, the two negatives make a positive. So I h bar cubed over 2m times d cubed psi by dx cubed minus I h bar v d psi by dx, right? Okay. Then, oh Jesus, okay. I'm just going to combine these two minuses to make a plus. So plus, and then, yeah, okay, hang on. I'm going to get rid of that minus, make this a plus. So what's this going to give me? Minus I times h bar cubed over 2m d cubed psi by dx cubed, right? Plus I h bar v, because v has no, well actually, you know, yes it does, I'm an idiot. I h bar, and then chain rule, partial v with respect to x times psi, plus v partial psi with respect to x, like that. Okay, nice. These two terms cancel out, so that's negative I h bar v partial psi with respect to x, plus I h bar partial v with respect to x psi, plus I h bar v partial psi with respect to x. These two terms cancel out, so finally we're just left with this term right here. So if I move that up, right, let's just copy this down. So this is going to equal I over h bar times integral negative infinity to infinity psi star times I h bar partial v with respect to x times psi. So the h bars cancel out, the two i's make a negative. This is going to give me the expectation value of the negative of oh, whoops, that's not a psi, that's supposed to be a v, my bad. So negative partial v with respect to x, and this once again is something we proved up here, right? D by dt of the expectation value of p is equal to the negative of the expectation value of partial v with respect to x. In this case, d by dt of the expectation value of p is indeed equal to the negative of the expectation value of partial v with respect to x. And with that, I believe we are done with problem 3.18, and now we can move on to 3.19.